All right, so this this lecture we're going to talk about linear systems, and this will be part one, and we'll do part two next time. This has nothing to do with trig, but this is part of the syllabus of Math 92, so it's something that we need to talk about. All right. Um, so in this section, we're going to talk about how to solve linear systems in a very, very specific way. And this is the way you really should be doing them in this section for example, the homework problems. Um, this way is very important because the way I'm going to be describing this algorithm that I'm going to be describing is very, very close to how you would actually be doing them in real life. The deal is you probably or possibly already know how to solve linear systems, at least theoretically, or at least you know some process of doing it. But oftentimes the way people first learn this, it's very ad hoc. You kind of just take a look at the equations and you try to figure out how to manipulate them to make things match up and cancel and stuff like that. But the way I'm going to describe it is very algorithmic, which means it lends itself really, really well to programming up onto a computer. And in real life, that's what you do, because in real life, the problems that you work with are huge. So maybe a million equations and a million unknowns. You're not going to be able to do those by hand, so you have to program them up in a computer. And if you want to do that, you need a solid algorithm that the computer just follows, the same procedure every time, every step, as opposed to, what we normally do when we do things by hand, where we look at the problem and we, maybe we work with this variable in this step and that variable in the next step, depending on the structure of the equation. Here, we just do it algorithmically, almost no brains involved, which is kind of nice because, again, it lends itself really well to programming. All right. So let me first introduce what linear systems are. I'll say a couple words about why we care about them, and then we'll get into our algorithm. So a linear system of equations is something like this. Let's just do it with an example. So 2x plus 3y equals 7, 5x plus 6y equals 10, right? And the idea is to solve for x and y. So this guy here is called a linear system of equations. It's a system of equations because there's more than one equation. It's a linear system because we have x's and our unknown quantities, our x's and y's, don't interact with each other. There's no, for example, what I mean by that is there is no x times y or x over y or anything like that. Notice there's no powers of x and y's. It's very simple. It's just a constant times x plus a constant times y equals a constant. And then the second one is a constant times x, constant times y equals a constant. All right. So these are in a way, the most simple kind of equations that you can work with multiple unknowns. But of course, we can extend this kind of problem to as many unknowns as we want and as many equations as we want. And we'll be doing some analysis of those kinds of problems in part two. By the way, so we're doing linear systems. The kind of one, so this is two variables, x and y, and two equations. The kind of one variable and one equation version is just something like 3x equals 5, something like that. All right, but that one is kind of so simple that we don't talk about it at all. It's really when we get to multiple equations and multiple unknowns where things get interesting. Or not interesting, but maybe interesting and complex, complicated. All right. So you probably or possibly have learned how to kind of solve these guys in the past. Let me just look at this particular one: 2x plus 3y equals 7. 5x plus 6y equals 10. And maybe I think a lot of people, the way they learn this is they're taught to notice the 3y and the 6y, and they know that if I multiply the first equation by 2, like multiply every term in the first equation by 2, then what I'm going to get is this is actually the same as 4x plus 6y is equal to 14, right? Because if I multiply an equation on both sides by the same thing, it doesn't change the equation. And then what I do is I take this equation and my second equation, and I subtract the two. And so what's going to happen is 4x minus 5x is negative x. All right, so subtract. Let me call this 1 star. This is my original 1, and this is my original 2. This is 1 star. Subtract 2 from 1 star, right? What I'm going to get is 4x minus 5x, which is minus x. 6y minus 6y is 0, and that was the whole point of multiplying by the first equation by 2. And then 14 minus 10 is 4. And so I immediately get x is equal to minus 4, right? And then once I have x, I can plug the x value into either equation 1 or equation 2 to get y. So let's plug it back into equation 1. So 1 would tell me 2 times negative 4 plus 3y is equal to 7, which tells me minus 8 plus 3y is equal to 7, which tells me 3y is equal to 15, and so y is equal to 5. All right. Okay, so this is one way to solve this equation, set of equations, and it's perfectly legal. But like I said, it's in a way not algorithmic in that, right? What we did was we noticed that the two y terms kind of are work very nice together, in that I can multiply the first one by 2 and then subtract, and the y's would go away. So the way we're gonna kind of learn how to do this right now is gonna be very, very much more algorithmic. So let's actually do this. Let me start with 3 equations and 3 unknowns, because the 2 equation, 2 unknowns, our algorithm will work perfectly for it, but there's only going to be a couple steps, and I really want to show off how to do this, you know, step by step, and how things look as you move from one step to the other. Okay, so let's do one with 3 variables and 3 equations. And you'll notice that this week, all our equations are the same number of, all our systems are the same number of variables as equations. But we'll talk about what happens if we have a different number of equations versus variables next time. And there's really interesting and really super, super important analyses of these situations that we'll talk about next time. Okay, so let's solve this system of equations. So in other words, I want to find x, y, and z, so that when I plug them into equation 1, 2, and 3, I'm going to get that they satisfy all 3 of them. All right? Okay, so the way we're going to do this, again, is very, very algorithmic. So what we're going to do is we're not going to, in a way, like examine y and z and see how they interact and stuff like that. We're just going to look at, actually, let me label these, sorry, first of all, 1, 2, and 3. So we're just going to start always with equation 1. And then what we're going to do is we're going to use equation 1 to get the x in equation 1, the first variable in equation 1. We're going to use that guy there to get rid of the x's in equation 2 and 3. All right, so that's our short-term goal. All right, so it's very similar to what we just did in terms of the y's just now. But again, this is very algorithmic. We're not going to look at the y's or the z's. We want to do it just with the x's. All right. Okay. So again, this is because, right, for example, if you're programming this up on a computer, you're not going to tell a computer sometimes look at y, sometimes look at z. And then if you do that, because if you do that, you're going to have to tell the computer when to look at y, when to look at z, right? And that's a huge pain. Why complicate everything? when you can just give a solid, concrete way that always works every time. All right, so we're going to use the x to get rid of this x up here, to get rid of the second x and the third x. So let's first use the first x in equation, or use equation 1 to get rid of the x in equation 2. All right, so what I'm going to do is I'm going to multiply first equation, so equation 1 by minus 2, and then add the result to equation 2. All right, and what's going to happen is replace equation 2 with the result, this final result. Okay, so I'm going to be multiplying this equation, first equation, by minus 2. I'm going to add it to the second equation, and then that's going to give me, a new equation. That's going to be my new equation 2. All right, so I'm going to replace equation 2 with the result of this this description right here. Okay, so let me call this step. Let me just put a dot here, a bullet point. Okay, so let's do this. So if I multiply equation 1 by minus 2, so what I mean is multiply all the way through by minus 2. What I'm going to get is minus 2x plus 4y minus 2z equals minus 2. All right, multiplying equation 1 by minus 2. Let me write that as minus 2 times equation 1. All right, so we'll next time I'll have a kind of formal notation for this, and it'll be we'll also make this algorithm a little more efficient in the organizing of data. All right, but the algorithm will actually still be the same. All right, now the reason why we did this multiply by minus 2 is because we noticed equation 2 had 2x. So if I do this, right, and I write down equation 2 right under equation 1, I'm going to have 2x minus y minus 3z equals 14, right? And if I add the two equations, in other words, I add them term by term, what's going to happen is the minus 2x and the 2x are going to cancel, and so the x's will go away. So I end up with 3y minus 5z equals 12. All right. So this guy here is going to be, this was equation 2 here. This is going to be my new equation 2. All right. So let me update my work. So I had x minus 2y plus z equals 1. So notice something interesting here. Every step we do, only one line will change in every step. All right. So equation 1 did not change at all. Right? Equation 3 does not change at all. Minus x plus 3y plus z equals minus 8. Only equation 2 changes. Right? So this is nice in that, it's step by step, but also you're not doing too many steps in one go. And so things aren't as complicated, so you don't have as much chance of making a kind of silly mistake. All right, so the way I'm going to write our new equation 2, there's no x term. Everything I want to line up the y's and the x's and the z's so that I don't get confused with what is what. So I'm going to put the 3y here, minus 5z here, equals 12. All right, and I'll just leave a blank where the x was. But that blank is really, really important. That blank right there was the goal. Okay. All right, so that's the end of step 1. Step 2, I'm going to do exactly the same thing, except the interaction will be between equation 1 and equation 3. I'm going to use equation 1 to clear the x variable in equation 3. So I'm going to, let's see. So here I'm going to multiply, always I multiply the equation that I'm using to clear the other equations in this situation, the first equation. I always multiply something to that one, and I always add it to the other equation. All right, so we just want to keep it consistent. We don't want to sometimes multiply to the third equation and add it to the fifth equation. We don't want to sometimes multiply to the first equation and then subtract the fourth equation, right? So we're always consistent to make it nice and simple, number one, and to also make it nice and simple in terms of programming it for a computer. because it's always the same algorithm every single time. All right. So always multiply something in this first kind of sequence of steps. Always multiply something to equation 1 and add it to the other equations. All right. We did that to equation 2. Now we're going to do it to equation 3. All right. Now, of course, you'll sometimes notice that maybe it's easier, depending on the structure of your equations, um, maybe it's easier to work with equation 2 and then use that to clear equation 1 or something like that. We're not going to do that. We're only going to do it algorithmically. All right? Because again, we want to work very, very algorithmically as if we were a computer. All right? Where the main goal is not to actually solve equations, but to learn how this algorithm works. All right? Okay. Actually, I promised I would say a few words about why this was important. Let me do that now. Just a couple words. So in real life, a lot of problems, let's say weather prediction, just as a typical example, of a very, very hard problem, um, cannot be solved perfectly. So you can't just write down the equations and then solve the equations and get a perfect answer. Because the equations are really, really unpleasant. The differential equations that pop up are really hard to solve, or sometimes impossible to solve by hand as a formula. So what you need to do is you need to use a computer to estimate or approximate the solutions, right? And when you do that, or how do you do that? Oftentimes the way you do it is you take your difficult problem and in a way transform it into a problem that a computer can work easily with. And computers work very, very easily with these kinds of problems, linear systems, right? Because if you just think about the algorithm that we're going to be doing, it's very straightforward. So you convert your super hard problem into a linear system, and then you tell the computer to solve the linear system, and then that gives you answers which are an approximation to the real life problem, right? And so that's one explanation for why weather prediction is not perfect. It's because everything when you do the weather prediction, it's an approximation, and so there's going to be when you approximate, there's going to be errors, and when you're doing a very complicated problem like weather prediction, the errors can accumulate and cause errors, big errors sometimes in your prediction. But if you've noticed, as time has passed over the decades, weather prediction has gotten better and better and better because for one reason, for many reasons, but one reason is because we have better and better computers to be able to solve these problems more and more accurately, allowing us to have better and better weather predictions. All right, weather prediction is just one example. Almost every problem, in a way, that we can solve, that we need to work with in real life, is a differential equation. You'll learn about those in calculus, in maybe third or fourth semester calculus. And those differential equations can almost always be converted to a linear system of equations, which pretty much always can be solved on a computer. And so that's why these systems are so important, or at least one point of view for why they're so important. These days, linear systems are also important in many other aspects. For example, artificial intelligence. All right, but that's kind of our quick motivation. So again, it's not that we were trying to learn, how to solve a system, right? If I gave you 4 equations and 4 unknowns right now, you probably could solve it using whatever ad hoc method you learned in the past. But what's really important is the algorithm, because you really want a computer to do it, because you're not going to be able to do a million equations and a million unknowns by hand. So you need to program it up into a computer. So you need a concrete algorithm. Okay, so let's do step 2. We're using equation 1 to clear equation 3. And here, what do we multiply to equation 1? We don't have to multiply anything because we notice if we add equation 1 and equation 3, the x's will go away. All right, so I'm going to write this as multiply equation 1 by 1, then add result to equation 3. All right. Oh, sorry. And then I'm going to replace equation 3 by the final result. Okay, so that's my step 2. Actually, I think we'll probably do the kind of more efficient, not efficient, the kind of simplified method in this lecture. I think we'll have time to do that. All right. Let's see. So if I do that, then when I add, let me actually kind of write this out just as I did the previous step. This is my equation 1. This is my equation 3. And if I add them together, I'm going to get these two cancel. These two add up to y. These two add up to 2z. These two add up to minus 7. All right. Okay, so this is my new equation 3. Okay, so my set of 3 equations before now becomes x minus 2y plus z equals 1. No change. Second one, 3y minus 5z equals 12. No change. And then only the third one changes. So that was, this guy right here, right? So we get y plus 2z equals minus 7. All right, so this is the current state of our problem. And one thing important to note here is, of course, when we do this procedure, what's happening is that every set of equations at the end of every step, like this one here, is equivalent to the one from the previous step. All right, so this set of 3 equations and 3 unknowns is equivalent to this one up here. All right, and this one up here is equivalent to our original set of equations and unknowns. So what that means is if we can solve the final one, the same solutions will solve the first one. And the point of doing this procedure is that at every step, the problem gets simpler and simpler and simpler. And so what will happen is by the final step, our problem will be super simple. We'll be able to get the answer really quickly. And then that means we've solved the first equation, our original horrible looking equation, very easily by the end. All right. And you can even notice at this point, the equation that we have at this point, the set of equations that we have is simpler than our original one, right? There's no term here and no term here. Okay. So in a way, what you can notice is in this bottom corner here, we have just 2 equations and 2 unknowns in a way, right? So what we started out with was 3 equations and 3 unknowns. But what we have here now is, if we just look in this box, 2 equations and 2 unknowns, right? So this set of equations and unknowns here we have is actually significantly simpler than what we had originally. All right. Okay, and we'll actually see how everything works in the next step. Next, so the idea was essentially we've used this x up here to clear everything under it. All right, in terms of kind of the picture of what's going on. All right. Okay, so our next step is to go to the next variable, which is y. And we're going to use the next equation, which is equation 2. So we're done with equation 1. It's finished. We're not going to even touch it until towards the end. All right. So now we're going to focus on this corner here. So we're going to use this second equation here to clear the third equation. All right. All right. What I mean by that is this 3y, we're going to use that to clear everything under it. All right, so we're going to use this 3y to clear that y right there in equation 3. And if there was an equation 4, we would use 3y to clear the y in equation 4, and so on. All right, so we always want to clear, when we were working with x, we were clearing everything under that first equation. Now we're going to clear everything under that second equation, and so on. You keep going until you get to the end, which we'll see very soon. All right. Okay, so I'm going to use the 3y minus 5z equals 12, equation 2, to clear that y in equation 3. So again, our algorithm, you always do it the same. You multiply something to the kind of the base equation that we're using to cancel the other guys. So this is the second equation. So we multiply minus 1/3 to equation 2 and add result to equation 3. All right, and then new equation 3 will be the result. All right. So y minus 1/3, because I notice if I multiply minus 1/3 to 3y and I add it to y, well, minus 1/3 times 3y gives me negative y. And then when I add it to the y's will cancel. All right, so let's do this. So minus 1/3 to equation 2, that gives me y minus 1/3. So plus 5 over 3z is equal to minus 4. All right, and then I'm adding that to equation 3. Okay, and the whole point of this addition is that these two y's should cancel, and they do. And when I add the next line, it's going to be 5/3 plus 2. So that's going to be 11z. 11/3 z is equal to, and this 2 is going to add up to minus 11. All right. Okay, so this is going to be my new equation 3. So what I end up with is x minus 2y plus z equals 1, no change. 3y minus 5z equals 12, no change. And then our new equation 3 goes right here. That's 11 over 3z equals minus 11. Okay, so this is our latest, the latest incarnation of our problem. All right. At this point, notice we've cleared everything under the x's. We've cleared everything under the second line, the y's. And so our next step would be to go to the next line down, use this z, use this third equation to clear everything under it. All right, but there's no more under it, so that's where we stop. Okay, or stop part 1 of the problem. So now we go to part 2 of our algorithm. So this was part 1, to put our equations into this form. One way to look at this is it's like a stacked equation where that's kind of top heavy. The first variable has nothing underneath it. And then we go to the next line, the second variable has nothing underneath it. Then we go to the next line, third variable has nothing underneath it. And we continue that. If we had 10 equations and 10 unknowns, we would stack it in exactly the same way. But once we're at this point where there's nothing left to do, now what we're going to do is we're actually going to solve the equations. All right. So the way we're going to do that is we're going to go from the bottom up, because the deal is the last equation that we have here is the simplest one. All right. Okay. And this is where you'll see why we did all this and how this procedure made our system of equations into something super simple. So if I take a look at equation, again, let me label these. Equation 1, equation 2, equation 3. So this part is called, did I actually name the, I didn't, okay, sorry about that. I probably should call that part 1, but let me call this one part 2. So this one has a name. This is called back substitution. Actually, our first part has a name too. It's called Gaussian elimination, but let's not bother with the terms at this point. Okay, back substitution. So we look at equation 3. We go from the bottom up. So equation 3 tells me, it literally says 11 over 3z is equal to minus 11. And so now we solve for z. So this tells me z is equal to 3 over 11 times minus 11, which is minus 3. All right. So now that we have z equals minus 3, so let me write z equals minus 3, put that in the box. That's our final answer for z. Okay. So what we do now is now we go to equation 2. So we go again from the bottom up. The reason we go to equation 2 is now that we have z equals minus 3, equation 2 only has y's and z's. So if we stick in the minus 3 for the z, then equation 2 will only have y's, and then we can solve for y, right? So let's do this. So 3y minus 5 times, and the z is minus 3, so minus 3 equals 12. All right, just sticking in, again, z equals minus 3 into equation 2. All right, and as you'll notice, right, there's only y's in here, so we can actually solve this for y. 3y plus 15 equals 12, which tells me 3y is equal to minus 3, which tells me y is equal to minus 1. Let's put that in a box. That's our final answer for y. All right. Okay, now that we have y and z, we go up to the next level, which is equation 1. All right, and as you'll notice, equation 1 has x, y's, and z's, but we know z and we know y. So if we put in z equals minus 3 and y equals minus 1, we can get x, right? Because x will be the only variable left. So let's do that. X minus 2y, which is negative 1, plus z, which is minus 3, is equal to 1. Now we solve for x. So this is going to be x is plus 3, minus 3 is equal to 1, and immediately we get x equals 1. All right, and that's it. That gives me all my variables. If we actually had to go up more, then we would go up to the next step and then solve for the next variable and so on. Okay, so you can see this algorithm works where you can do any number of variables and unknowns, at least at this point where you have the same number of variables and unknowns, and get a solution. All right, that's not exactly true, but at least for this week it's true. We'll talk about complications to this procedure next week. All right, now of course, now that we have our solution, x equals 1, y equals minus 1, z equals minus 3, if we wanted, we could check our answer by plugging these three numbers into our original problem, right? If we plug them into this original problem, oops, where was it? Yeah, here. This original problem, we can check our answer, right? You don't want to plug it into an intermediate step because if you made a mistake before that, you wouldn't realize that mistake, all right? So you always want to plug back into your original problem. Okay, so this one happens to be correct. So so that's it. We're done. That's our core algorithm for solving these systems of equations. All right. Before I talk about kind of how to make this slightly simpler, at least in terms of organizing the data, let me say a few words about what you use to cancel, right? So let's say I had 3x minus 2y plus 4z equals 10, and then 5x plus y plus z equals 9, 2x minus 3y plus, and let's say there's no z, it doesn't matter. That's actually perfectly legitimate, all right? Okay, so for this problem, again, for all the problems, our procedure is to use this first line to clear out the guys in the next lines. And then when we're done with that, we use the second line to clear out the guys underneath that. All right. But I just want to do the first step just to make sure we know how to do the clearing. So if this was equation 1, equation 2, equation 3, our first step in terms of clearing is we multiply something to equation 1, add it to equation 2. All right. So what do I do in this case? I need to multiply something to equation 1 to clear equation 2. So the equation 2 has a 5x. So I need to multiply something so that I see a minus 5x, right? So to see a minus 5x, I multiply minus 5, but I have a 3x in equation 1. So to compensate for that 3, I divide by 3, All right, so what I would do is I would multiply, my first step would be to multiply equation 1 by minus 5/3 and then add to equation 2. All right, and that would be my new equation 2. Okay, so let's just do that just to see that it actually works. If I multiply equation 1 by minus 5/3, so minus 5/3 times 3 is minus 5, right? So we get minus 5x, and that's the key point. We need that minus 5x so that when we add it to the 5x, it'll go away. And then the rest of this is we just do the multiplication. So this is plus 10 over 3y, and then minus 20 over 3z is equal to minus 50 over 3. All right. The numbers might be horrible. There's nothing you can do about that. They just are what they are. I think maybe one way a lot of people learn these is perhaps they would multiply equation 1 by 5 and then multiply equation 3. Multiply equation 2 by 3, or let's say minus 3, and then add them. And then the first equation, if I multiply by 5, I'll get a 15x. Second equation, if I multiply 3, I'll get 15x. So when I subtract them, they'll go away, right? That's okay for doing by hand in terms of just learning it for the first time. But you don't want to do that in terms of the algorithm because, first of all, a computer doesn't care. See, the reason why we do this sometimes is because a lot of people are uncomfortable with fractions. And so if you do it this way, multiply by 5 and multiply by 3, you don't have to deal with fractions, right? But computers don't care about fractions, right? Computer can work with whole numbers just as well as easily as fractions. So there's no reason for a computer to want to do this, okay? Number 2, this is inefficient because when I multiply the first equation 1 by 5, how many operations do I have to do? I have to multiply this one to here, this one to here, this one to here, this one to here. All right. When I multiply equation 2 by 3, that to there, that to there, that to there, that to there, right? So 1, 2, 3, 4, 5, 6, 7, 8. 8 multiplications, right? I can kind of cheat and not do the first two, right? Because I know I'm going to get 15x and 15x. But 6 to 8, right? But if I do it my way, or the correct way, how many multiplications do I have to do? I multiply minus 5/3 to equation 1, right? To all of equation 1. So how much work is that? I do the first multiplication, 2, 3, 4. I only have 4 terms, right? So actually what you're doing is you're doing half as many multiplications when you do it the correct way versus the way you perhaps used to do it with whole numbers, all right? And this matters quite a lot when you have a million equations and a million unknowns, right? Instead of doing 2 million operations, if you did it just with whole numbers, you would only be doing 1 million. And that's significant in terms of real life problems, all right? So that's why we're working the way we're working, all right? This is actually, this procedure that we're describing here is actually the most efficient way to do this, to solve these guys for generic problems. So when you do these on homework, you really want to do it exactly this way, because again, we're not really learning, to solve the equation. We're not really trying to solve the equations. We're actually learning the procedure. That's the important feature of this week. All right, in any case, now that we've done that, right, if we look at equation 2, 5x plus y plus z equals 9, right, when we add them, the two terms will go away, and we'll just have y's and z's. All right, so 13 over 3y minus 17 over 3z is equal to 23 over 3, minus 23 over 3, right? Horrible, but again, nothing that that a computer cares about, all right? So our new equations can be 3x minus 2y plus 4z equals 10. Our new equation, that was our first equation, no change. Equation 2 becomes 13 over 3y minus 17 over 3z equals minus 23 over 3. And then equation 3, no change. Minus 3y equals 3. All right. And now probably you should pause and just think about how you would use equation 1 to clear equation 3 before I tell you. Okay, so if you were to do it, this would be multiply equation 1 by minus 2/3 add to equation 3. All right, why minus 2/3? Because the 3 in the denominator cancels with the 3 in the numerator, and the minus 2 allows me to have a minus 2x, so it cancels with the 2x. All right, and let's see that this works. We end up with minus 2x plus 4/3 y minus 8/3 z equals minus 20 over 3. Equation 3 was 2x minus 3y equals 3. When I add them, the first terms cancel, and that's the whole point, again, of multiplying by this specific number, minus 2/3. And let's see, when I subtract them, I get minus 5/3 y. When I add them, 8/3 z equals minus 11 over 3. So my step 2 would be, my equations would now be like this. 13 over 3y minus 17 over 3z equals minus 23 over 3, minus 5 over 3y, minus 8 over 3z equals minus 11 over 3. All right, so again, looks unpleasant. You're going to have to work with fractions. No escape. There's no escape from that. All right, now that everything under the first term here is cleared, now we go to the second equation and clear everything under it. So that means, in particular, using this 13 over 3y to clear the minus 5 over 3y. All right, and again, you should probably pause and quickly think about how to do it, what you have to multiply to equation 2 in order to do this before I tell you. All right, so the way to do it is multiply. So I want to end up with minus 5/3, right? So minus 5/3, and then I want to clear the 13 over 3. So divided by 13 over 3, or I can write this as times 3 over 13, same thing, right? I forgot to write the words. Multiply equation 2 by this, right? So this is actually equal to, just to simplify it a little bit, this is minus 5 over 13, or let me write it, minus 5 over 13, right? Add to equation 3, okay? And when we do that, we're going to end up with minus 5 over 13y, and then we do it for the rest of these. This is not going to be so nice, plus 39, 585, z is equal to 39, and this is going to be 115, something like that. All right, but the important feature is just the y's, right? The z's are just what they are. There's nothing, the z's and the other terms, they're just what they are. There's nothing you can do about them, right? But the important feature is that these two guys will cancel. So when I add these together, I'm only going to end up with z's, right? Something z equals something. And so that means I can solve for z. And once I've solved for z, I can solve for y. Once I've solved for y, I can solve for x, doing the back substitution procedure, right? On the last step. Okay, so that's the idea. You could do this with 2 equations and 2 unknowns. You can do this with 5 equations and 5 unknowns. You could do this with 1,000 equations and 1,000 unknowns. Exactly the same procedure. All right, just go step by step, very methodically and carefully. And that's the core algorithm that that we wanted to learn for this week. All right. And again, on the homework, do it exactly with this procedure. Don't swap rows. Don't do anything like that. Just do it straightforward, no brains, do the algorithm, all right? Again, you are simulating as if you were a computer, right? And a computer is certainly not going to be able to deviate from an algorithm that the programmer has given it. Okay. Oh, and if you are kind of interested in programming or doing any sort of computer engineering or anything like that in the future, or if you are doing it some right now, if you are learning some right now, might be a good idea just to program this algorithm up on a computer and see how simple it is as an algorithm, right? Okay, so let's talk about kind of how we can simplify this in that we're gonna organize our data kind of more efficiently, right? So the way I've kind of written all these up, right? It's a lot of writing, right? It's a lot of words. So let's do that first example again, except let's reorganize. So our first example was x minus 2y plus z equals 1, 2x minus y minus 3z equals 14, and then minus x plus 3y plus z equals minus 8. All right, so what I'm going to do is I'm going to do this idea of a matrix, and we are only going to be using matrices. Matrices are super important things in mathematics. They have very interesting mathematical structure that can be studied, and that structure can help you understand these kinds of problems here that we're working with. But for us today, right now, and for our class, we're only going to use matrices as a vessel for holding information more efficiently than what we have been doing. All right, but just remember, in the future, you might see matrices again, and they'll very likely be used in a very important way, where the matrices themselves have mathematical structure, and which leads to a lot of possibilities for analysis. Okay, so what I'm going to do is I'm going to notice essentially that, see, these x's and these y's and these z's, I don't really need to write them, right? If I just do this, I look at only the coefficients, 1, minus 2, 1, 1, right? Coefficient of 1, of x, coefficient of y is minus 2, coefficient of z is 1, and then this number here is 1. And I'm just going to copy them down. So the next equation, 2 minus 1 minus 3, 14. The next one, minus 1, 3, 1, minus 8. Right? Just copying down the coefficients. So if I write this guy here, this matrix here, carries the same amount of information as my as my kind of equations that I've written up here. The only difference is I have to kind of just remember in the back of my mind that the first column represents the x's, the second column represents the y's, and the third column represents the z's. All right, so that I can always move back and forth between the two representations of my system. Right? If I want to rewrite this matrix as a system, it's always whatever the number here is times x plus whatever the number here is times y plus whatever the number here is times z equals the right-hand side. All right, and here what we're also going to do is we're going to put a line here, to delineate the right-hand side and left-hand sides of the equation, the ones with the x's and the ones that are just constants. All right, this is technically called an augmented matrix. But again, we're not really going to be using this terminology too much in our class. All right, so this matrix here is, when I say, we're simplifying on the procedure, this matrix is what I mean, right? We're kind of getting rid of all the unnecessary bits of notation, all right? Okay, because again, the only relevant bits are the coefficients. All right, so let's do our procedure, and we're introducing more notation. I'm gonna as usual, I'm going to start with row number 1, which represents equation 1. I'm going to use it to clear everything under it in rows 2 and 3, and 4 and 5 and 6, if there are more, okay? I need to multiply something to row 1 and add it to row 2. Okay, so the notation I'm going to use, and you should probably be using this note, you should certainly be using this notation, is I'm going to multiply 2 times row 1, and I'm going to add it to row 2, and that's going to be my new row 2. All right, so row 2, the new row 2 is equal to 2 times row 1 plus the old row 2. All right, I probably, to be the most clear, you should write new row 2 equals blah, 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 old row 2. But this is kind of, in a way, like programming notation. A lot of, if you do code things, this is how you would often write it. So we'll keep the notation like this, all right? So my new row 2 will be 2 times row 1. Minus 2 times row 1, right? Because I need to actually add up to so that the first term is 0. Minus 2 row 1, all right? Sorry about that. And let's actually do that. So row 1 does not change. Row 2 doesn't change, so I'm just going to copy them down as is. But row 3 doesn't change, row 1 doesn't change, row 2 changes. Minus 2 times row 1 plus row 2. So minus 2 times this guy up here plus row 2. So that gives me 0 there. Minus 2 times minus 2 plus minus 1 gives me a 3. Minus 2 times minus 1, minus 3 gives me a minus 5. All right. And then minus 2 times 1 plus 14 is going to give me a 12. Okay. So what we had before was, when we did this, our new equation 2 didn't have the x variable in it. So that's represented by the fact that this is 0 here. All right, so we're looking for 0 right there. Next, we use row 1 to clear row 3. All right. So let me represent it like this. All right, so these arrows represent kind of the next step. Row 3 is going to be the row that changes. It's going to be equal to row 1 plus row 3, right? Something times row 1 plus row 3. It's always, again, something times the row that you're using to cancel the other rows, and then plus the other row. So you should never, ever have any number in front of the row 2 up here, nothing in front of this row 3, only things in front of this row 1. And in this particular case, it's just a 1 in front of the row 1, all right? Okay, so what we end up with is 1 minus 2, 1, 1. This one doesn't change. This one doesn't change. And then row 3 changes. Row 1 plus row 3. So that's a 0. Minus 2 plus 3 is a 1. 1 plus 1 is a 2. 1 minus 8 is a minus 7. Okay, now we're done with the usage of row 1 because everything under it is 0, right? Which represents the fact that there is no x term, there is no y term in the equations 2 and 3, or at least in the new equations 2 and 3. Next, that means we need to use row 2, or equation 2, to clear everything underneath it, right? So we need to use this 3 term right there to clear everything below it, all right? Okay, so that means row 3 will change. So row 3 changes. It will change by minus 1/3 times row 2 plus row 3, right? And so we end up with this. Row 1 does not change. Row 2 does not change. Row 3 changes. It becomes 0. So here's why we had to do the algorithm this way. I started with row 1 to clear the ones underneath it. What that did for me is that when I work with row 2 to clear the guys underneath it, this 0 right there and that 0 right there never changes. All right. So for example, imagine if I were lazy or something and I didn't clear this one here. Let's say I had a number right there, right? Then when I use this one to clear the next one, that number is going to go to there. And then this 0 will have been spoiled, right? So, sorry. So the fact that this guy here is 0 is actually very important. Okay, right? Because minus 1/3 times 0 plus 0 remains 0. All right. Okay, 0. And then minus 1/3, so this is 5/3 uh, minus 2. Plus 2, sorry. So 11 over 3. All right. And then this one is minus 1/3 times 12 minus 7. So that would be minus 11. All right. And again, our goal was to make that guy 0. If there were more lines underneath, we would use that second row to clear them as well. But this is essentially the structure that we're looking for, where everything up here, these guys can have numbers, but everything down here should be zeros. All right. So there's actually a name for this. This is called upper triangular, when you have a matrix where things below here are all zeros. And these are really, really good things because, as we've seen, right, they allow us to solve equations easily. Okay, so this is the end of part 1, right? How do we do part 2? I think the best way to do part 2 is just to translate everything back into variables again, just to make it easier to see what's going on. So, for example, our equation 1, 1 times x minus 2 times y plus 1 times z equals 1. Our equation 2 is 3 times y minus 5 times z equals 12. Our equation 3 is 11/3 z is equal to minus 11. All right, so let me write, sorry, we call this back substitution. And now we always work from the bottom up. We solve z, solve y, and then solve x. All right. So here, this is exactly the same as what we did earlier. No change. All right. Same as before. Okay. So really, the new feature was kind of this matrix representation of our equation, or system of equations, and this nice way of representing what we did at each step, which is super useful in terms of computing, let's say, on homework and stuff, because it's really, really easy to make mistakes computing these. And if you write down carefully what you did at each step, it's much, much easier to catch mistakes and to figure out where to fix them, so you don't have to throw away your entire bit of work if you do make a mistake somewhere. All right. Okay, and here again you can see, let's see, at this step here, let me do it like this. We started, let me say it like this. We started out with just a generic system of equations, 3 equations, 3 unknowns. But once we get to this step, after we've cleared everything under equation 1, this guy here is 2 equations and 2 unknowns, right? Because there's no more x's. And then once we've cleared everything under the second equation, this guy here is 1 equation and 1 unknown. So essentially the procedure was 3 equations and 3 unknowns becomes 2 equations and 2 unknowns becomes 1 equation and 1 unknown, which is easy to solve, which means the previous step is easy to solve, which means the previous step is easy to solve. So again, you see this theme in math where you're making a difficult problem into easier, smaller and smaller problems. 3 equations, 3 unknowns becomes 2 equations, 2 unknowns, essentially, becomes 1 equation, 1 unknown, essentially. All right. So you can imagine, right, if you had 10 equations and 10 unknowns, it becomes 9 and 9, then 8 and 8, then 7 and 7, all the way down until it's 1 and 1. That one's easy. So you can solve the previous one, which was 2 and 2, then the previous one, and so on. All right. Okay, so we'll kind of continue this discussion next time, because the way I've described this, right, everything looks cool, everything looks straightforward, there's no problems or issues with the procedure, and that'll be the same for the homework for this week. But next week we'll see that secretly there are potential issues, and we'll talk about what happens when we do encounter them.